Okay, I think we can start now. So I'll start with a short introduction of David. So we are, of course, very happy that you are able to give this first webinar, and welcome also to everyone else. So David received his PhD from Cambridge in 2011, and then went on to Harvard for Sagan and a Menzel fellowship, and has now joined the faculty in Colombia. So his calling is actually in the morning there. So we're happy that you could come so early. So of course, David is of course most famous perhaps for his work on exomoons, and his PhD title was Transits of Exoplanets with Moons. But he has also been working on a lot of different aspects of transit light curves. And it is one of those aspects that he will talk about today. So please, David, go ahead, and we'll see.
Thank you. Yeah, thank you, Alexis. Slight correction: I didn't do my PhD at Cambridge. I did my undergraduate at Cambridge, and then my PhD.
Where was your PhD then?
Yeah, before leaving to Harvard. So yeah, I guess mostly I've been spent half my time I spent thinking about exomoons and working on the HEC project, but one of the other big things I'm interested in doing is very precise light curve analysis for many reasons, for trying to infer parameters as precisely as possible, for looking for atmospheric features, for example, for measuring transit timing variations. And also recently I've been working on techniques to measure the eccentricity of exoplanet orbits just through photometry, which requires a very precise measurement of the shape of the light curve. And all of those things are influenced by limb darkening. The other reason why I like this problem is just because mathematically it's kind of simple and elegant and attractive to me. And that's how I sort of started getting interested in this. So I will start my slides. And this first slide, I'm not going to explain, but we'll come back to this image later, and hopefully it'll make more sense later on. So mostly I'm going to be talking about fitting transit data for limb darkening coefficients. So very briefly, I'm sure everyone here knows this, but I'll just in case, I'll have a recap of limb darkening. So it's merely an optical effect where the center of the star is brighter than the limb. And what's happening here is that geometrically the path length from a certain specific layer, which has a temperature, within the star is greater near the limb, which is kind of illustrated in this figure. I don't know if you can see my mouse. Can you see my mouse? Anyone? I think you've all muted yourself.
Yes, we can see you.
Okay. Great. So yeah, this path length near the limb is obviously is the same as this path length here, but it's coming from a lower temperature part of the star than this part. So this area appears brighter is essentially the effect. Okay, so this is seeing the effect with a typical image, and this is taken from the Netherlands, and you can see that the limb is obviously darker for the sun than it is near the center. So here's a little cartoon illustration of that. So the important thing is that it's circularly symmetric. It's spherically symmetric in 3 dimensions, but circularly symmetric in projection. So the intensity profile has this symmetry, and that's important because there are certain darkening effects, such as gravity darkening, which are not circularly symmetric, and that makes the problem much more challenging to model. However, also for gravity darkening has some advantages in that you can look for the spin-orbit alignment actually between a transiting planet and the star. Obviously, if it's circularly symmetric, you don't have that information. So limb darkening is both simpler mathematically to model, but it doesn't have quite as much power, let's say, as gravity darkening might have. But gravity darkening is quite rare. It's very rare that you see this. Okay, so this is a typical intensity profile as measured from radial distance. And I think I illustrate that here, yeah, with R. So R's defined as being less than 1. So I'm using units of the stellar radius where 1 is touching the limb. And you can see the intensity just sort of naturally drops off. This is just an arbitrary shaped intensity profile to illustrate that. And it's darkening as you go from the center to the edges. What I'm not going to talk about is brightening, limb brightening. And this can happen. It's kind of rare, but you can see it, for example, from chromospheric emission lines from silicon 4, which were Schlauin et al. Wrote about in 2010. They saw some tentative evidence for that from a transiting planet. So in principle, you can, for certain narrow bandpasses, have limb brightening. But for missions like CHEOPS, Kepler, TESS, which are broad bandpasses, and they're looking at main sequence normal stars, you're almost certainly going to be talking about seeing limb darkening effects. Limb brightening is very rarely seen. If you did see limb brightening, the light curve looks quite different. It would look W-shaped rather than U-shaped. But again, I'm not going to talk about that too much today. Okay, so with that caveat out of the way, I want to talk about how we mathematically model this feature. So first of all, we have this radial distance r, but we very rarely talk about r. We usually talk about an angle called mu. So as you look at the star, you're seeing some certain projection from the edge, from the limb, which would be here, and you're looking at some distance r. Obviously, the radius is set to 1, and therefore the angle here, let's call it theta, can be written down as 1 minus r squared, all square rooted, for the cosine of that angle. And we normally talk about cosine theta, which is rewritten as mu. So normally when we talk about limb darkening profiles, we parameterize them in terms of this mu angle rather than r. I don't really know why. It's just sort of something which the literature is doing. It really doesn't have too much bearing. It's fairly easy to switch between these two variables here and here. They're very closely related. But it does mean that the intensity profiles tend to look like this. So you have to appreciate that when you're looking at this mu angle, 0 is actually near the center of the star. Sorry, 0 is now near the limb. We've kind of flipped it around. So 0 is near the limb and 1 is near the center of the star now. So it's brighter near the center, as you can see here in this intensity profile. So you kind of have to do a little bit of a mental switch, which I sometimes fall over on when you're translating between r and mu. But as I said, most of the time we actually parameterize it in terms of the mu angle. Okay, so these are some light curves taken by Heather Knutson back in 2011 with Hubble, and they beautifully illustrate the limb darkening effect for transits. So you can see this is taken with the STIS spectrograph, and I think they split it into, 10 different wavelengths here, and going from something like, I guess this is around sort of 800 nanometers down to about 300, 400 nanometers, and you can see the limb darkening effect becomes way more pronounced as you move towards the blue end of the spectrum, which is, the colors are more or less representative of the wavelength here. So this is fairly common. As you move towards the infrared, limb darkening becomes very negligible. And if you're modeling Spitzer light curves, for example, you really don't have to be overly concerned with limb darkening effects. If you have a mission such as Kepler or CHEOPS, which is using a visible bandpass, then you can expect to have, be in this regime where you're going to have very significant limb darkening effects, and it's causing you to have these U-shaped transits. One of the biggest problems is that if you look towards the red end, you can see the contact point between the second and third and fourth, which I'm sort of moving my mouse over here. You can make them out, they're fairly clear. And if we went towards the infrared, this would basically be a flat line in the bottom here, and you'd have a very sharp transition, just as you have a sharp transition on the first and fourth, and third and fourth. Sorry, the first and second, and third and fourth here. So as you increase the amount of limb darkening, that discontinuity, that step, becomes more and more smoothed out, and therefore it becomes harder and harder to pin down where exactly the planet fully enters the stellar disk, which is what this moment in time corresponds to. And that has very important implications. If you can't measure this very well, or at least it's degenerate with the limb darkening shape, then it's going to limit your ability to measure things like the inclination angle and ultimately the semi-major axis and stellar density of this star. We can actually measure the stellar density of a star based on this shape. But it's very important that you can measure these moments in time to do that. So these are reasons why we should care about limb darkening. Obviously, it's chromatic, which has a big implication for people doing atmospheric retrieval of the exoplanet. So you will quite easily get the wrong transit depth if you, apart from these contact points, just the actual depth itself you can see is changing as a function of wavelength. And that's virtually all due to limb darkening here. So if you model your limb darkening wrong, you're going to retrieve the wrong transit depth, and therefore you're going to think that there are atmospheric absorption features in the annulus of the atmosphere of the exoplanet, which are not really there. So this is extremely important for people who are trying to retrieve the atmospheres of exoplanets. But as I alluded to, it's really not just atmosphere people who should care about this. I mean, fundamentally, you are getting the wrong planetary radius. And even if you're not doing spectroscopy and you're just trying to follow up a planet, getting the wrong planetary radius is pretty much the most basic reason why you do a transit analysis. So it's kind of fundamental that you're really not retrieving the one piece of information you probably care about most if you don't model limb darkening correctly. Other things such as the impact parameter, which is a proxy for the inclination of the orbit, the semi-major axis, which is a proxy for the light curve drive star density, also come out wrong if you do not model the limb darkening correctly. So you have to deal with this carefully, and that's just to stress this point again. It's especially true for transits observed in optical bandpasses. Of course, if you measure in the UV, this would be even more severe. But we don't really have at least very much, transit measurements planned in the ultraviolet wavelengths. So how do we model this? I'm going to walk you through a little argument here. First of all, we usually, when you're modeling a transit, you want to infer the planet parameters. That's pretty much the reason why you're measuring this transit in the first place. And that requires fitting the light curves to a model. And therefore, you also, if you're going to model the light curve, you of course have to model the intensity profile. So just to point this out very basically, you have to model the intensity profile to model a transit. Since the transit model is nonlinear, especially for any model having limb darkening included, then the fitting routines that we use, doesn't matter if they're Bayesian, it could be frequentist, can be even at least squares, are going to require making many steps. If it was a linear problem, you can just actually use the normal equation and invert the matrices and just solve in one single realization what the right answer is. You can't do that for a nonlinear problem, which this is. You have to take multiple guesses, typically at the very least sort of 10 to the 2, 10 to the 3 models. And then if you care about actually measuring uncertainties precisely, then you're probably going to want to do better than that and use something like a Bayesian MCMC. And that's going to require 10 to the 5, 10 to the 7 simulations. So each model simulation needs to be really quick. That's kind of an important requirement when we're modeling transit light curves. So at each step, at each of these 10 to the 7 simulations, let's say, you could, if you wanted to, run a full 3D stellar atmosphere model at every single simulation and see what the intensity profile should look like, given some inputs, such as maybe the effective temperature of the star, the mass of the star, things like this. But rather than do that, because that would be extremely time consuming, we tend to adopt these parametric, in inverted commas, laws. I don't know why they're called laws. They're obviously not laws. It's kind of a misnomer. But yet this is the language we're stuck with. And these parametric laws are designed to sort of be polynomial-based models, essentially, which encapsulate most of the behavior predicted by these atmosphere models. Okay, so let's focus on that point. So for example, the quadratic law looks like this. So what we're looking at here is intensity profile as a function of mu, which is this angle I talked about earlier, or the cosine of the angle I talked about earlier. And it's parameterized by these two coefficients, u1 and u2. And you can see it's just a quadratic expansion. So we call these coefficients the limb darkening coefficients, or I'll probably abbreviate them to LDCs quite often in this talk, just to save me keep saying this mouthful. And in the paper I wrote, we often talk about them as LDCs as well. It's fairly common to refer to them as that. So you have to choose these LDCs. Let's say, it doesn't really matter which law you use. You can use the quadratic law, you can use a linear law, whatever law you use, you have to somehow assign what are going to be my limb darkening coefficients. U1 equals what? Is it 1.0? Is it 2.5? You have to assign a number to each of these coefficients. So there's two approaches. The first is theoretical on the left, and on the right I'm talking about fitted. But to start off with the theoretical model limb darkening coefficients, the idea here is that you run a sophisticated stellar atmosphere model that could be 1D, it could be 3D. People have been arguing over that recently, over a grid of plausible inputs, so things like the effective temperature, the metallicity, log G, etc. And then you create a a table, a catalogue available online somewhere that the community can use of all of these limb darkening coefficients for every possible law that you think is reasonable and for all the possible stellar inputs. So you have these massive files being uploaded. And obviously they're grids, so you typically, to actually use these, a common approach, very common approach, is for an observer to take the maximum likelihood stellar parameters. So essentially, what is the best effective temperature? What is the best metallicity? And then they input those numbers into the grid, and they interpolate typically, or I guess the worst thing to do would be to do a nearest neighbor. That'd be the simplest thing you could do. Interpolate these grids and try and estimate what is the limb darkening coefficients at that best set of parameters. And then they just fix the limb darkening coefficients to that choice in every single simulation they do. That's typical. There's pros and cons to that, and I'll talk about that in a moment. Sometimes observers will interpolate the grid on the fly, which are, so every single step of their Monte Carlo MCMC or whatever it is they're doing, they will actually re-interpolate that grid over and over and over again. And the interpolation is different because they draw the stellar inputs, these parameters here, from, say, a Gaussian prior. I don't think I've ever seen anyone do anything other than a Gaussian prior, and they're independent Gaussian priors, which is also, might not be the right thing to do. Is TF truly independent of metallicity when you make these measurements? There's reasons why that's a good idea and a bad idea, but I'm not going to go too much into those. The other approach, which is kind of different philosophy here, is to actually fit the limb darkening coefficients. So you actually are measuring them, really. You're taking the transit light curve data, and you're going to measure what is U1 and what is U2. You're going to get a posterior for them ultimately. Typically, the application of this is limited to linear and quadratic laws. In fact, I've never seen, although maybe someone could correct me afterwards, I've never seen anyone attempt to fit anything more complicated than quadratic law set of coefficients to a light curve before. People usually assume the limb darkening coefficients have uniform priors, or they might use some linear combination of the limb darkening coefficients in order to minimize the correlation between the two, because these parameters are correlated, and that slows down your MCMC. So quite often people do a transformation of the two. Sometimes observers, and I've done this before, have attempted to construct informative priors on the limb darkening coefficients based on the stellar grid models. So you basically do this step, which I talked about here, again, before you actually run your MCMC fed. So you take some Gaussian priors for these guys, you interpolate thousands, millions of times onto the grids, and you create a prior distribution of what you expect U1 and U2 to look like. And you might even use this trick as well at the same time, use a linear combination to minimize the covariance, which is how I did it. And then you have an informative prior limb darkening coefficient. So you're still kind of fitting them, but you're constrained by what the models tell you. In either case, it's important to note that you have to choose a law. You have to choose linear or quadratic or cubic or whatever the hell you're doing. You have to choose one of them. You can't let it be like a model. The model is flipping every single time that you do an MCMC, or at least I've never seen anyone do that. So let's talk about some of the advantages and disadvantages of this. The advantage of doing the theoretical limb darkening coefficients is that you do often actually know something about the star, or at least you think you do. And if you've been measuring this star for a long time, then you have constrained the effective temperature very precisely. And why shouldn't you use that information when you're trying to model the light curve? It makes sense to propagate that knowledge. It's also simpler because, especially when you're fixing them, you really don't have to fit for these parameters anymore. So you're reducing the number of free parameters in your fit. Although I have to say that's generally not a huge advantage these days, because fitting 5 versus 7 free parameters really isn't a big deal. I mean, we can easily fit 7 free parameters to a data set. So it's actually more important if you're fitting exomoons. In exomoons, you have 14 free parameters. So if you can reduce a couple of them, that would be advantageous, although I have to say I've never done that before. But for those sorts of problems, it might make sense to try and reduce the number of freedoms. The disadvantages of doing this approach is that, do you really trust your stellar atmosphere models? Stellar atmosphere models are are being produced by different groups, and they don't always agree with each other. They're using different techniques, such as 1D, such as 3D models. How they're modeling the interior of the stars and the convection and the atmosphere is variable. And so when you're choosing one stellar atmosphere model, then you have a model dependency, which is sort of locked into any results that you obtain. And that's because the limit darkening coefficients are covariant to all of the other parameters you care about, like I talked about at the beginning. So you have a model dependent result, which you can either say, I trust my model and that's fine, or I don't trust my model and that this concerns me. Of course, in general, we're always doing, just as a philosophical point, we're always doing model dependent stuff. I mean, we're modeling it as a Keplerian orbit around a star, which is spherical, the planet's spherical. So there's always model assumptions. It's just a question of which of those assumptions do we trust and which one do we not trust. Finally, if you fix the limit darkening coefficients just to one particular value, I think this is not a great idea, because it's essentially equivalent to assuming omnipotence about the star's intensity profile. You know, so you know it perfectly. There's absolutely no uncertainty, 100% precision, or in other words, a Dirac delta prior, which from a Bayesian perspective is deeply troubling, that you could ever think that you know something to infinite signal to noise. Although practically speaking, there may be reasons why you think this is okay, but certainly from a statistical perspective, it's troubling to do this. So what about the fitted approach? Well, first of all, the beauty here is that we get around this model dependency problem. So the results are independent of how well your stellar atmosphere models are doing. This is important because, you know, you might think you're looking at a single star where you think you know what the atmosphere is, and you're actually looking at a binary star system, and the planet's not even going around the star you thought it was going around. So even though you have a great spectra and you think you know the effective temperature, there might, in some cases, I can imagine it being possible that the planet is not going around the object you think it's going around. And therefore, assuming that you know the stellar atmosphere really well is actually a really bad assumption. And you get around that by fitting limit darkening coefficients. And you can actually perhaps look for that. You can actually use the information you're gaining as a test for this hypothesis. The other nice thing is the ignorance about the true intensity profile is propagated into all parameter uncertainties. So in a way, you know, you're being more conservative. You're allowing your measurement uncertainty on the limit darkening coefficients to be part of your ultimate error budget on your planetary radius. And you know, there are many exciting things you could do by actually fitting these things. You could potentially test theoretical models. You could build empirical catalogs and use this information rather than treating it as a nuisance parameter. The downside is it's time consuming, more free parameters, but again, I think this is not this is fairly minor. It does not use any knowledge of stellar parameters into the fit. I think this is actually a fairly salient disadvantage to point out. You know, I talked about this binary star system, but there are cases where you really, really are sure it's going around the star. You think it's going around, and you know that star really well, and you're not using any of that knowledge or information if you just blindly fit the limit darkening coefficients. And that's kind of a shame, because potentially you could fit the planet's properties more precisely. The other big disadvantage here is that naive sampling, so you just randomly choose a U1 and randomly choose a U2 and see how good the fit looks, that would usually produce an physical intensity profile. And I'll talk about that in more detail going forward. So out of these disadvantages, I'm just going to say, you know, this one's so what? I mean, time consuming, it doesn't really matter if you takes an extra hour or two to fit a light curve. I think this is, especially as computers get faster and faster, this is increasingly not such a big problem. This one, there are potential solutions. You can try and build informative priors, but you might also ask, you know, do you trust your stellar parameters anyway? So this one's sort of salient, but it's maybe a case-specific issue. And this one is the one I'm going to talk about really in this talk to finally get to it. And this is one I can solve. That naive sampling of limit darkening coefficients produces unphysical profiles. You can actually get around that by reparameterizing your limit darkening coefficients. So this crazy simulation here is just choosing, and I think I'll have to replay this because I didn't introduce it. This is just choosing a random U1 for the quadratic law. a random U2 for the quadratic law. And I've just gone in a box between -3 to +3, -3 to +3. And this is what I mean by naive sampling. So you just guess a random point and you see whether the profile is physical or unphysical. And I'm defining a physical profile to satisfy these two conditions. It's everywhere positive. So these are intensity profiles plotted on the left. So you can see some of the intensities are negatives, and negative fluxes obviously doesn't make any sense. This is unphysical. And monotonically decreasing from the surface to the lip. So remember, this is the center of the star at mu=1, and this is the lip. So we expect it to be decreasing, dropping down from right to left. And if it doesn't do that, or if it has sort of it curves back up again or something like this, then it's unphysical. And just to replay this simulation, this is just 1,000 random points that you're picking, and you can see that the vast majority of them are just going to be completely unphysical. So you only really want points which are in the green region, which are the physical limb darkening coefficients. And you can kind of see it looks like a triangle already. So you want to draw from that triangle. Even if I made this, I'm drawing from a very big square here. Even if I made this square as tight as possible, which it might look like, where my mouse is going now, you can see that's still going to be only 50% efficient, because half of that parameter space is red and half of it's green. So even if you could tighten that box down, which you can do quite easily, you're still going to be only at 50% efficiency. So let's look at these two constraints I talked about. You can express them mathematically. So we're basically saying the intensity is greater than 0, but all mu between 0 and 1, and the di dmu is greater than 0 for a monotonically decreasing profile at all mu. So taking this and taking this gives you this constraint, and you can evaluate this at two extremes when mu=1 and mu=0. And that tells you that 0 is less than 1. Okay, great. That's not very constraining. And this one tells you that u1 plus u2 is less than 1. So that's an interesting constraint that you're measuring here. So you always know the combination, the sum of them is going to be less than 1. So we'll save that one as a useful constraint. And doing the same thing over here, and again evaluating these limits gives you two new constraints this side. So just from these two conditions, you derive 3 analytic criteria on the limb darkening coefficients. In the case of the quadratic law, I'm not talking about any of the law here, just the quadratic law. It turns out you can do this for virtually any two-parameter law. So whether it's a square root law and a linear term, whether it's an exponential and a log term, whatever it is, you can always play this trick and measure some constraints. And they tend to be bounding. Although I think in the exponential case, it's not. That's actually an unbounded case, by which I mean these three constraints do not form a nice triangle like we had before. And I'll visualize that here. So this is the green points basically that I showed you before. So now you can see these three equations we've derived, these three constraints plotted as sort of contours almost on this plot, and you can see that we're really nicely bounding this region. So in an ideal world, when you fit a limb darkening, when you fit a transit light curve for limb darkening coefficients under the quadratic law, you really only want to draw a sample from this space, because drawing a sample anywhere else is unphysical. Why is that a problem? Well, first of all, it doesn't make any sense. Second of all, if I move slightly down, and let's say I make the profile now be monotonically increasing, that's going to change the U-shaped transit to slightly inverted U-shaped transit. And there's reasons why in a low signal to noise environment that a Monte Carlo fit might think that's a perfectly acceptable fit. So you have the MCMC accepting steps, which correspond to inverted transit profiles, basically, which you know is not the case for sure. Just based on the fact it's a normal star and I'm using a wide bandpass. So therefore, your error on your radius, your error on your impact parameter, all those things is going to be increased more than is necessary, because you're exploring parts of parameter space here and here which are excluded. So it really makes sense to not explore this space. And you could do that by a rejection algorithm. You could every time test, are these three criteria satisfied? If they are, accept it. If not, reject it. But that means, if it's a low signal to noise environment where the MCMC is happy to explore all over the place, then you're going to be rejecting something like 50% of your trials just due to this effect, let alone likelihood constraints. I want to point out this angle. This angle is about 36 degrees along this dimension here, along the sort of the bisector of this triangle. There's an interesting paper from 2008 that Andras Powell wrote, and he talked about doing a principal component analysis. Actually, he did a Fisher analysis, I think, in the paper, but it's essentially an analytic way of doing a PCA, principal component analysis, which is the objective of doing these types of analyses is to try and find out what linear combination of my parameters is going to minimize the autocorrelation, not the autocorrelation, the correlation between each of them. The reason why that's important is because if you can use a PCA to rotate your parameters around and reparameterize things, then you can make your MCMC faster. So what Andras Powell said is that you should use an angle of about 35, anywhere from 30 to 40 degrees, as shown in this figure, to avoid correlations between the Lindau-Darkening parameters for the quadratic law. So he's saying he doesn't really know why. He doesn't really talk about why it's 30 to 40 degrees. He just sort of notes it as a result of his analysis that use an angle between here and you will minimize the autocorrelation. And you actually see why this is. So here's a natural explanation as to why 30 to 40 degrees is the optimal range. Because now your MCMC is wandering up and down this triangle along this bisector. And if you can find a way to reparameterize so that you're sampling always from this triangle, then you will naturally eliminate these correlations between these two terms by essentially moving up and down this bisector. And that's what my proposed parameterization does, in fact. So it's kind of interesting that this pattern was not noticed before, but it really naturally explains this behavior that Andras Powell noticed. Okay, so you can actually reparameterize this triangle fairly easily into a right angle triangle just by a change of variables. So I'm using V2 and V1 and defining them by these two expressions here. And you can sample from a right angle triangle with 100% efficiency using a trick from computer games, basically. So it turns out in computer games, they often build models such as, let's say, if you're modeling a person in a computer game, like a computer game character, and their face is actually made up of millions and millions of tiny triangles, and they're slightly twisted and slightly oriented to each other. And the way they fill out those triangles is by using this reparameterization trick, which is shown here. So I didn't invent this, I just found it. Don't ask me why I was looking at a computer games book, but I found it in a computer games book that you can use this trick. So using this, you can actually sample from the triangle here perfectly, 100% efficiency every time. So I was very appreciative to notice that. So this is the final reparameterization in terms of the original U1 and U2. So I suggest that you fit for Q1 and Q2, and these are bound on the interval 0 to 1. And just by the fact that these two being between 0 and 1, you're always going to sample a physical Lindau-Darkening coefficient, 100% of the time. So this, and it also covers 100% of the physical parameter space. So it's 100% valid and it's 100% complete. So it's really the perfect inversion. You can also invert these here using this term. So let's say you want to make a posterior for U1 and U2 rather than Q1 and Q2. You'd use these equations to flip that. So just to compare this to other parameterizations, it's kind of weird that everyone else had basically put a rectangle on here and had not put a triangle. So naive sampling is just this square here, the dotted black line. And if you just naively sample within this square, and notice that I've made that square as tight as possible to include all of the triangle region, then you're only going to have 25% efficiency, in fact. So 75% of this is just white unphysical space. Looking through the parameterizations, actually Tim Brown et al. In 2001 with the HST paper they wrote, suggested a linear combination of U1 plus U2 and U1 minus U2. It's very common reparameterization. That's shown in the brown rectangle. So if you look at this brown rectangle that my mouse is sort of tracing out here, you can see that does a pretty good job, but there's still lots of white space. And actually, that's only 50% efficient, which is this number here. Epsilon is 50%. And then there's been other suggestions by Matt Holman, which is actually much worse, Christopher Burke, and even a paper that I was on and I suggested back in 2011, so 2 years before I worked on this paper, which was a slight modification. That's 50%. So essentially all of us, myself included, were guilty of basically proposing four-dimensional shapes rather than a three vertice shape, which is really what you need here to sample this parameter space. So obviously this one is 100% efficient. So I would argue whether you want an informative prior or an uninformative prior, it really doesn't matter. You should use this parameter space, and I would encourage people making stellar atmosphere models to use this parameterization for their grids, because it's so trivial to test that your set of parameters are physical. It's between 0 and 1 in that set, and you know you're in physical space. And then we could build informative priors that way as well. So this is a strong argument for using this parameterization for quadratic laws. However, are quadratic laws actually such a great thing? Are they accurate enough? So the atmosphere people kind of argue about this as to how well each of these different polynomial laws, in inverted commas, does. This is from Magic 2015, and they're comparing the results from a 3D atmosphere model, which are the points. That's the actual things which have been produced by the atmosphere model, and comparing it to the best fitting sort of linear law, quadratic law, etc. And virtually everyone always finds that the 4-parameter law, not surprisingly because it has more parameters, always does the best. And they argue that here. And the quadratic, which is what the dot dashed one, it's kind of hard to see, but I think it basically fails near the limb of the star, as you can see here. It doesn't pick up this power near the limb. So this 4-parameter law was proposed by Claret, and it's kind of the gold standard. It's the most accurate law that we have for describing. This one always passes the tests pretty much from atmosphere models. It's also true, not from an atmosphere perspective, but from a data perspective, that quadratic law is not always good enough. So if you look at this data, Heather Newton actually tried to fit these 4 quadratic laws, and that's the residuals that you get when you fit it with a quadratic law. It's not good enough. There's significant power left over. And the black line here is showing you sort of the residual between the fitted quadratic coefficients and the theoretical Claret 4 limb darkening coefficients. So the theoretical model actually does do a good job, and once you get it to 4 parameters to explain this profile. The quadratic law is not good enough. You have significant residuals here, which are going to obviously lead to getting the wrong parameters for this exoplanet. So can we do better than quadratic? And I think we have to. Yes, it's simple for me to play this trick on it, but it's not accurate enough for many applications. So it'd be nice if we could do it on this. Could we play the same trick I talked about on this nonlinear law than as I did for the quadratic law? As before, naive sampling of these coefficients is a really bad idea. Virtually all of the time, so that should be a C3 there. And that should be a C4, I'm sorry for the typos. Virtually all of the time, you're going to sample an unphysical limb intensity profile by just randomly guessing these 4 coefficients. It's going to be even more exacerbated once you increase the dimensionality of the problem. So can we play the same trick that I played for the quadratic? And remember, a key way that I solved that problem, at least me personally, was to visualize the parameter space, was to do that Monte Carlo simulation and see where's the bad points, where's the good points, and notice that it was a triangle. And I really just literally noticed it was a triangle by eye. That's what I did. And then reparameterized it into a triangle. So the problem I have here is that I can't visualize for all parameters. I can't visualize 4-dimensional space. So no, I'm not able to draw a shape in that dimension, which constrains the region. But as a three-dimensional being, I am able to imagine three-dimensional space. So let's see if we can find some three-parameter law rather than a four-parameter law, which does more or less as good of a job as possible. And David Singh was very important in showing me a way to solve this problem. In his 2010 paper, he argued that you can actually drop this first term here, and that's motivated by his sort of some papers on solar data, 3D atmosphere models, which essentially show that the intensity profile varies very smoothly at small mu, which means that this term doesn't really matter that much. It doesn't have that much constraining power. So David Singh proposed that we drop that, and this is the Singh-style three-parameter law as a result. So it's just the same thing here, again with the same typos. I apologize, that should be C3 and C4. But essentially we're just killing this term that it's a reduced version of the nonlinear law. So this law is tractable because I can imagine three dimensions. So this is good. Okay, so let's apply these same two conditions I talked about before, everywhere positive and monotonically decreasing. It turns out just using those two is not enough. It doesn't bound the box. It kind of scales up to infinity as to the range of reasonable parameters. So I had to invoke something else, and I invoked that there was a negative curl at the limb. So this is essentially saying that the intensity profile kind of is asymptotic near the limb, that due to foreshortening effect, that it very rapidly drops off. So it'd be nice to sketch it, but if this was my y-axis and this was my x-axis, I'm going towards the limb, I expect the intensity profile to sort of drop very rapidly down, is what I'm expecting when I impose this condition. And when I impose that condition, I can constrain the parameter space. By the way, this condition is always satisfied by theoretical models. So I looked at the catalogs that David Singh was producing and checked whether this condition was actually holding for his catalogs, and it is always, or at least in the vast majority of his cases, over 95%, I think this is satisfied. So this is one of the reasons why I thought this was a reasonable thing to do. So this is the parameter space. I'm going to show this as a 3D plot, but I have to open this to show you. So this is the parameter space of allowed points. So ignore the coloring. So green and red, just imagine that the same thing. This is the allowed region using those three constraints. And you can see it kind of looks like a disk as you sort of twist it round, but it's actually slightly thicker. There's like a thicker edge here. As you move up, it gets thinner. So actually the thickness of the disk, if you can see it here, is thinner near the top than it is near the bottom here. It gets wider. So it's not quite a perfect elliptical disk. There's something going on here. And it also seems like it gets thinner down here, and then it gets wider again here. So there's some interesting geometry to the shape, and it's difficult to see it because the disk is so flat. So the first thing I did was to try and sort of reparameterize these terms here to try and squash this disk down so I can visualize it a bit more easily. So what I did is I rescaled the axes to put it inside a unit cube, and then I rotated it round until two of the axes aligned, two of the envelope axes aligned with the Cartesian axes, basically. And that's this plot here. And again, I'll open the 3D version to show it a bit more clearly. So now, I mean, that's that same parameter space, but just slightly squashing and rotating things around. And you can see it looks like a cone, especially the green points. I will explain the difference between the green and the red towards the end of the talk. But you can see that the green points almost perfectly look like a cone. So this is encouraging. So if we have a cone, that's a regular shape. And yeah, what you can do is actually twist that cone up again and rescale again. And now you can actually put the cone with its apex pointing up, which is what I did here, into this new parameter space called G. So I'm moving up the alphabet in different parameter spaces. And then finally, once you're in this cone, you can sample from a cone and make it a cube. So I'll just quickly show those two as well. So here's the G parameter space, which again, now is the cone sat on its apex. And you can see it really does look just like a perfect cone, apart from those red points, which are the anomaly on the edge here. And then if we look at the cube, it looks like this. So what I've done between these two is there is actually a very efficient and easy algorithm to sample from a cone. You essentially just draw a radius, a height, and then you draw sort of a polar coordinate from within the disk. And then that essentially is going to sample a random point from within this cone. And then using that recipe, you can actually just transform it as a cube if you wanted to instead. So if I draw a point from within this cube, I'm always going to essentially be producing one of these points from this disk. So this is this initial parameter space I started out with, C, C3, C2, C4, as you can see here. That is the same parameter space, well, it's the same points as this, but just reparameterized. So alpha R, alpha H, and alpha theta are just a linear combination of these three parameters. And now it looks like a perfect cube, which is really easy to sample from, of course. It's just a uniform prior. You'll notice there's kind of a hole here. Maybe you can see that. There's a little hole poking out. So there's this cube. If I sample from this cube a small amount of time, I'm going to draw a point which is in this hole. And that point is not actually a physical point. So that would be an unphysical Lid-Darkening coefficient that I would sample. But as you can see, it's kind of rare. It's a relatively small amount of the volume. And that's a shame. It's not perfect, but the point is it's very, very good. It's something like 95% of points drawn from within this cube will be within the physical boundary conditions I initially defined. And then I'll talk about these red points now. So yeah, I basically made this a Borg cube, is essentially what I've done. So what are these points? So all the points satisfy the 7 analytic criteria. So from those 3 boundary conditions I started out with, I derived 7 equations, and all of these points satisfy those 7 equations. In green, I actually modified those equations very slightly in order, actually artificially, I chose them to make this more symmetric because I noticed the cone wasn't quite a perfect cone. So I actually manually tweaked the equations to make it look like a perfect cone. So I gave myself a more symmetric loci. So I have a modified set of these criteria. And the points which satisfy the modified criteria are green, and the points which only satisfy the original criteria are red. So that means I'm excluding a small region of space, which is reasonable. And I'll quantify that in a moment. So ultimately, this is a constraint. You can only sample from a perfect cone. This space here, you can't sample from. I mean, you can see it's very complex. So you can't, there's no simple algorithm to sample from this space, but if we assume it's a perfect cube, which it more or less is, or a perfect cone in the other parameter space, then it's easy to sample from. So this is the actual reparameterization I used, written down, which again is mostly the conal sampling. So this is 94.4% complete, by which I mean that if I draw a point from within that green cube, 94.4% of the time it's going to be a point which satisfies the physical definition of an intensity profile. 5.6% is missed, and that's these red points. So those red points are missed by sampling from the cube because they stick out of the cube. So we're not going to be able to sample that region. So if you strongly suspected your staff, for whatever reason, happened to have an intensity profile in this very extreme, weird thing sticking out here, then you would miss it by using this parameterization. But that's kind of a fact of life here, I'm afraid. It's also over 97% valid. So remember in that green cube, there was a little hole. Let me show it again. There was that little hole. Where is it? Just there. That little hole means it's not 100% valid. So if I draw a point from within the cube, sometimes it's going to be an invalid point if it lands in that little hole. And that's where this 97% validity comes in. And that's because I actually modified my criteria again. So it turns out it's actually really easy to test whether a point is 100% valid or not. So the remaining 2.7% of points can be easily removed with a simple rejection test, which is fully analytic at the end. And that's one thing which my code actually does. So you draw a point, which is 97.3% valid, and then you test just to make sure it is 100% valid or not, and get rid of those points which are not. So that way you're always drawing 100% of the time a physical limb darkening point. The only thing we're not accounting for is this, that 5% of the time there is a 5% volume which this parameterization will never explore. So you will never be able to explore this region, these red points, with this parameterization. So the code is public to do this. It's up on GitHub, on my Git. You can use this for doing the inverse and the forward transformations. And it also has that code for doing that final check as to whether the samples are physical or unphysical. And I've already shown those. Let's go forward. So this is my summary slide. So I think I did okay in time. So essentially, accurate treatment of limb darkening is super important for driving accurate radii, inclination, and cell densities, especially in the optical band passes. Fitting limb darkening coefficients is a really effective strategy because it propagates all your ignorances, and it essentially has model independence. So you don't have to have 100% faith in your stellar atmosphere model. You can actually test the atmosphere models. Perfectly efficient and perfectly valid sampling of quadratic limb darkening coefficients is easily done by using a simple reparameterization, which I proposed in 2013 with Q1 and Q2. So if you only care about quadratic limb darkening, it is a perfectly solved problem. We have a perfect solution. If you think that quadratic limb darkening is not good enough for you because you're doing high precision space-based photometry, then you need to use something like this, like the 3-parameter Singh law instead, which works by introducing an extra term. Naive sampling is horrendous, less than 1%, so you definitely don't want to do that. However, through some geometric transformations, you can approximate the loci of allowed points to being like a cone, and you can sample from the cone very efficiently. With an efficient, well, essentially you're sampling, just to reiterate it one more time, 95% of the time you are drawing a point which lies within the total allowed region, and over 97% of the time you are drawing a point which is going to be valid, and you can actually bump that up to 100% validity by doing an extra test on the end, which is extremely fast to run. And all the equations and code are publicly available, and I'd be very happy if you used it, and send me questions, and I'm happy to help explain anything that wasn't clear. So I can take questions now as well.
Thanks a lot, David. It was great.
Yeah.
I think everything worked great, at least from my end.
Yeah.
Now we can take questions. I don't know exactly how to do this. We have, let's say, 27 participants. But I guess I don't know how to moderate this. I guess you can just ask a question, and whoever asks first get to ask it. So if you have any questions, please go ahead and unmute your microphone.
I have the questions. I can start. Is that okay?
Yes.
Yeah.
Okay, right. So I would like to understand, I mean, we always mention that there is a lot of stellar variability that may affect the careful measurements on the limb darkening. I wonder if you consider this, all the macro turbulences and spots, all these that may affect the shape of the light curve.
Yeah, no, this is a homogeneously sort of spherically symmetric intensity profile. So therefore, if there were inhomogeneities such as star spots or granulation effects, I don't think granulation usually affects a light curve at this level, but let's say star spots certainly does, then you would need to model that separately or additionally. So essentially when you have a star spot, my approach, sort of thinking on the spot here, would be that I would model the light curve using the recipe I've just described, and then usually a star spot crossing, for example, is pretty obvious. You can can see it in the data. It looks like a triangle poking up in the bottom of the transit. And I would model that star spot crossing with an additional piece of code on top of this layer, essentially. So therefore, all of the out of spot stuff you're modeling with this profile, and then just where the spot crossing is happening, you use an extra bit of code to model that. Ben Sebecki, who's at Harvard, actually put a piece of code up to do that. So on his website, so there are codes available for modeling spot crossings. If it's an unocculted spot, that's harder. That tends to only dilute the transit depth, so it just makes it shallower. So if you knew that there was unocculted star spots, which is a challenge to know that you have them, then you can actually easily model it just by a wide dimension transformation. You basically just squash the light curve a little bit. Actually, sorry, it stretches. It makes the transit depth bigger. Wrong way around. It's like an anti-blend, an anti-contamination factor. So it stretches. So it's just a slight stretching factor that you apply if it's unocculted. If it's occulted, it's a real problem. And other than that, more complicated stellar activity that you can think of, basically no, it's a simple answer. This wouldn't account for that.
Thank you.
Anyone else? Okay. If not, then I thank David again.
Well, I have one question. Sorry, I was slow.
Okay. Please go ahead, Chris.
Just question, you show this reparameterization to be able to draw from a cubic or square distribution, but how do you make it such that it's afterwards homogeneous in space of your real parameterization, or don't you get
Yeah, that's a really good question. And I didn't have a slide on that, but I think I have a plot which might show what you're asking. So this one. Yeah, so this is a comparison of the, in gray, that gray histogram is the probability distribution of C2, for example, that you would get if you just drawed a uniform C2 point and then tested whether all the limb darkening coefficients were physical or unphysical. It would look like this gray histogram. And in purple, that smooth histogram is what you get from my reparameterization. So if you sample using the alpha parameterization and then convert back to C space, what does the distribution look like? It looks like the purple one. So it matches really nicely. So basically, you're not introducing any bias as you would. It's the same as basically doing a simple rejection test every single time, but it's way, way more efficient. So it's going to reproduce the same prior that you would have if you just did uniform, uninformative sampling and then did acceptance rejection on the end of it.
Okay, thanks.
Can I also ask a question?
Sure.
Yeah.
Yeah, I'm Hans Teg at ISC, Instituto Astrofísica de Canarias. You had a very nice slide at the beginning where you listed the advantages and disadvantages of either keeping the limb darkening values fixed or keeping them free.
Yeah.
Yeah, I did recently see a solution which I found quite nice, and was in the paper by Motalebi on the transiting Earth-like planet on the very bright star, HD 219, etc. That came out end of July. And they basically used the prior knowledge from the star characterization, the TF, and the metallicity with the errors. And from that, they basically, in the MCMC, they fed in TF and they fed in metallicity. And then they looked up from the Claret table the corresponding limb darkening parameters. And I don't remember if they used quadratic or they could have also used any higher order law that is tabularized in that work. And I think that is a very nice solution because you always have realistic parameters of TF and of the metallicity, and you don't have to worry about the limb darkening coefficients getting unphysical.
Yeah, I did mention that actually.
What do you think about that?
But so this is actually mentioned. I went over it quickly, so that's probably why I didn't explain it very clearly. But essentially, here one thing people sometimes do is interpolate the stellar grids on the fly for every single simulation, drawing from independent priors on the stellar inputs, which are these, which is, I think, is what you're describing, what they did. So yeah, people do that. Just so you're looking at the screen. So it's just this box here. So I think that's what they did. They did this box. That's fine. The problem with it is that normally you have to assume Gaussian priors, independent Gaussian priors on TF, metallicity, and log G. So
yes, but I think that makes sense. You know something about the star.
Yeah, so you're assuming you know something about the star, but you're assuming the TF is completely independent of metallicity, which is usually not a great idea. So you could get around this. A really big improvement would be if people measuring TF and metallicity use Bayesian encodes and actually delivered posteriors of TF and metallicity, which they very rarely do. Usually when people list effective temperature, they just tell you it's this plus or minus this, which gives you no alternative but to assume a Gaussian prior. But what would be great is if the community actually provided the posteriors of their effective temperature, the joint posteriors of all three parameters, and then you could build really truly informative priors on darkening that way. Although you still, just to be sort of plain devil's advocate, you still have the issue that you're assuming whatever stellar atmosphere model you're using is perfect, which, you know, there's no model error essentially propagated. So your model might be slightly erroneous by doing that. So that's one of the benefits of fitting. But I agree that's a much better approach than fixing for sure.
Okay, thanks.
Okay, so I think we should stop here then. And I have tried to record this talk. So if you missed something and want to watch it again, we'll try to post it at the CHEOPS website somehow, and we will get back to you on exactly where it is and where the next webinar will take place. So thanks to everyone, and especially David for giving.
Thank you for having me. Yeah, I enjoyed it.